Okay, let's take a look at another example where we have a data set. Let's consider data from the U.S. Energy Information Administration regarding characteristics of power outages across the U.S. Each row of the data set represents an observation of an electrical power outage. These 38 observations make up a sample from a larger data set. So these outages are collected all over the country for several years, and we've just collected a sample from that population, and that sample size is 38. So let's just take a look at some of the columns that we can collect from these data. The first column is just an ID value that I made up myself. Okay, so that's really not meaningful in any way other than to describe each of the outages. The second column describes the area affected by the outage, some kind of geographical location that's very specific. The third column represents the broader region where that area is located, and I just made that up myself. So we have some regional way to describe the outage. The next column is the root cause disturbance that led to the outage. So what was the initiating event that caused the outage in the first place? The next column is a dichotomous. Dichotomous is another word for 0 or 1, a binary variable that represents if the outage occurred during the day or at night, where 1 represents an outage that was initially caused during the day. Okay, so 0 then would be the outage was at night initially. The next column is the loss caused by the outage in megawatts. The next column after that is the customers affected by the outage, the number of customers affected by the outage. And then finally, we have the duration of outages in hours. Okay, so we could ask a lot of different questions. We could use our methods of finding confidence intervals, estimating the population mean of several different variables in this data set. For example, what's the mean duration of electric power outages with 95% confidence? So we want a way to estimate the mean power outage, and we know that a point estimate's bad. We don't want to just take a sample point estimate and use that to describe the population mean. We actually want to build a 95% confidence interval for that. So let's do that. What do we know so far? Well, first we need to go to Excel and find y bar. Okay, so what we're going to use in Excel is the average function again. Okay, so we're just going to use this average function across the data range for the column associated with the duration of the outage. Okay, and we're also going to use the standard deviation function. Okay, so we're going to input here the range of values that we want to calculate the standard deviation for, and again that's in the duration column. I really encourage you to play around with these functions in Excel. And Excel has a lot of functions that are very useful. Make sure you understand, whenever I type in average, what is Excel looking for in these in the parentheses. Okay, that's very important to figure out. So we want a 95% confidence interval. Therefore, alpha must be 0.05. Okay. Whenever we implement this average function, what is it we get for y bar? Our sample mean, okay, the sample of those 38 observations. What is the mean duration? We get 42.08 hours. Okay, what's the sample standard deviation from this standard deviation function? We get 44.31 hours. Okay. And what else do we know? We know we had a sample of size 38. Therefore, the degrees of freedom is n minus 1, 38 minus 1, which is 37. Okay? So our degrees of freedom for this problem, 37. Again, we're going to be implementing the t distribution to help us with the confidence interval. Therefore, we need a degrees of freedom. But it might be that the t-table doesn't contain 37 degrees of freedom. This happens all the time. Just depending on what our sample size is, we may or may not be able to find the associated degrees of freedom. One rule of thumb is if we only have a t-table, we can round down to the nearest degrees of freedom in the t-table and just use that t-value. Or we can use Excel. Okay, so if you're lost on a desert island, you don't have Excel, you don't have a laptop with you, but you do have your stats book, you can always estimate this by just rounding down. But if not, if you've got Excel, we can use an Excel function, and that Excel function is the T inverse function. Okay? So T inverse wants two things. It wants a two-tailed probability input, followed by a comma, and then the degrees of freedom. Okay? What this two-tailed probability means is that that's essentially alpha. We have a confidence interval that has alpha over 2 in each tail. Okay? That total alpha is 0.05. So this two-tailed probability is 0.05. Okay? If we want t of alpha over 2, then we need to input the two-tailed probability, the total alpha. Okay? Again, I encourage you to take a look in Excel and play around with the help function in Excel to see what exactly is you need to be inputting here. For this particular problem, we're going to use the T inverse function because we may or may not have 37 degrees of freedom. The two-tailed probability, 0.05, and degrees of freedom here, 37. Okay? And if we use Excel to find this, we'll get that the t value is 2.026. That is t of 37 degrees of freedom, 0.025 in the tail is 2.026. Okay? So now we have everything that we need to calculate this confidence interval. That confidence interval, again, y bar plus and minus t degrees of freedom alpha over 2 times s over root n. Okay? If we plug everything in, we've got 42.08 plus and minus t alpha over 2, 2.026 times s 44.31 divided by root 38. We had a sample of size 38. Okay, whenever we do that, we get that the lower bound is 27.52 and the upper bound is 56.64. Okay, and this is measured in hours. Okay, so what's the punchline here? We have a 95% confidence interval within which we think the true population duration lies. Okay, we are 95% confident that the true population duration of outages lies between 27.52 and 56.64 hours.